Hello and welcome. I'm Bill Wake. We're working on the regular expression matcher generator. It's basically a compiler for regular expressions. So it's all based on this article, Sequential Circuits from Regular Expressions Revisited by Doğan Ulus. And there's a link there if you want to get a copy for yourself, but we'll work through the theory of it anyway at some point here. All right, so our goal is you're going to feed in a regular expression of some sort. It goes into this matcher generator and code comes out. The example from the paper is C++. We'll write Swift and we'll start with something similar to this and see if we have time to evolve it a little bit. Okay, so today we got about halfway through or a third of the way through the parsing. Once we finish parsing, hopefully it won't take too long, we can implement the skip, out, and trigger functions and then generate some code. So let's go ahead. So we have a classic compiler, lexical analyzer or lexer, a parser, semantic analysis, code generation, intermediate code generation, and then final code generation with an optimizer optionally in the middle. We're limiting ourselves, so I'm combining the parser and semantic analyzer. We'll take a regular expression in, we'll build a parse tree, we'll annotate it with skip and out, the two functions that we'll see in a little bit. And then we'll take that and generate what's called a trigger set. And the trigger set is what you need to generate code. So we'll go from there. Where we are, we have a grammar for our regular expressions. If you have questions on the grammar or whatever, let me know. But basically I took an ambiguous grammar that defines what to do, but it relies on the intuition about how to match things up and stuff. Instead, I have a grammar that's useful for recursive descent parsing. And basically, the process is you make a method per rule. So there's going to be a parse function, an expression function, a term function, a unary function, a factor. Each one's going to return a tree, so a parse tree. If you're matching a character literal, you just return that, or you match it and return that in the tree. If you see a rule name, like a term goes to unary, then you call the rule. So term function, we'll call the unary function. If you have a choice, you got to use whatever character you're looking at to decide. So the unary rule, you write a factor followed by star, plus, or question mark. And, which character you use determines what it is. And whenever you see a repeat, which is either a star or a plus, not in quotes, you are going to use a while loop or a repeat loop of some sort. Okay. And then we'll get to the theory piece of this a bit more as we once we get past the parsing. But basically, you take your regular expression coming in, like A, B, or B, star, B, A, and then first thing you do is number the position, so 0 in front of everything, and then 1, 2, 3, 4. That's all on an A and 5. Those are all positions on the letters in the thing. All right. Then we generate this trigger set table. That says when you see an A, if you're in position 0, 2, or 3, it's okay to move to position 1. All right, and you can kind of see that in the grammar. At 0, you're starting in the front. If you get an A, yeah, that's a legit transition from A to the position between A and B. If you were in 2, then you have this option of a star, in which case you're sort of like back at 0, and you can do an A. And same thing for 3, you just at the other branch on the star. And each of these rules comes like that, and we can turn that into code fairly directly. Okay, thank you for joining me. I checked just before the show. I'm at 49 followers, so if you want to become my 50th, even if we get 3 or 4, you can each convince yourself you were the one that put me over the top, right? But there's a follow button on the corner, so take advantage of that. And also my website, xp123.com, the update gives you an option to sign up for a mailing list. Weekly, I put out blog articles. Generally, during the month, I write more programming kind of topics. And then the first week of the month, I tend to write something that's more focused on either user stories or more general agile topics. I've had one come out just today on replacing the template method, which uses inheritance, with the strategy pattern. So that's the sort of stuff you get. All right. Okay, we'll come back to numbering. Let's see. So we are let me get our environments. All right, so we have two compilers running. One is Regi, is the one we're working on. It takes a regular expression and produces code. The code it generates, I guess I can just kick this off. If I compile something, it shows up in the matcher.swift area down there, okay? And it's sort of a pseudo, we wrote some just kind of trashy code, but it copies it to my paste buffer. And if I go over here and I replace the matcher method with what was in my paste buffer, the code we compiled and generated through our compiler, and I run, I get a matcher for ABD. Okay, so over here, so the blue one is our compiler, the green one is the runtime for the result of the compiler. So if I do ABC and I check, nope, not a match, but ABD, yeah, okay. So what we've done so far, I mentioned we handle the factor, we handle basically we have expression. Let me get over to Parser. Okay, so we have a parse method that looks for an expression and then an end of text, and then we have a factor method, well, expression method that calls factor instead of term and unary and all those. Okay, and factor is prepared to handle letters or parenthesized expressions. So again, when you want to match a constant character, you just skip over it. You look for it, you make sure it's there, and then you skip over it, and then you call an inner method expression, which gives us our nesting. And then when you get back, you're going to check for a right parenthesis, and in which case you just skip over it. So you can see the choice behavior, you can see the calling a function behavior. We don't have any repetition yet, but we'll get some soon. All right. Let's see. So I guess the grammar is probably what I should keep in view for us. There we go. All right. So we got parse expression. Expression goes to factor, but I would like to build up these other things as well. So I'm thinking, let's just build up from the bottom and punch it through. I just want to get it moving. But the thing I think we see first is we have our tree. If you're just matching the factor, okay, we have the value in the tree. Let's see if we can get to our tree up at the top here. Okay, it holds the value, so it knows if you said A, it should look for A. Okay, but that's not really the way we need it to be. I don't know. I've been chewing over this in my head, which is probably a bad place to do it. But sort of the traditional pattern for this is every type of operator, basically, or leaf gets its own class, and they all inherit from a common class. Okay, and so I've got tree, but I'd really like to have a class that's, I don't know the right word for this one. It's either leaf or letter match. Maybe it's a letter match. And it has these things in it. And then down here, I'm going to make a letter match. And a letter match. Okay. And these things, I guess we've certainly got to inherit tree, and then we'll just pull these up. Okay, I think that will give us, hopefully that's the only changes we need. No, it looks like I don't know what well, okay. I don't really need the value. I don't know if anybody's looking at them yet. Let's just try it without it and see if anybody's looking. No, okay. So we will provide it. We'll make an override here. And I'm going to provide a dummy one. Okay, just to kind of prove there's something there. Doesn't need the override. Okay. And is that all we get? All right, let's. Okay. I would have rather extracted out a function or something like that, but okay. Now you could say, oh, maybe this should be a protocol, and maybe you'd be right. We'll come back on that one. All right, so with that now, my factor produces a letter match. In this situation anyway, okay. And let's let this one just do tree. Okay, I don't know if we're not really going to use the parse tree. Okay, I meant to do you. of an error situation. So I don't doesn't really matter, I guess. I just hate having to make everything optional all the way up. Let this be an error situation. Okay, let's move in and let's see if I got a quick way to get here. Yeah. All right, let's implement Unary and make expression call Unary. Okay, so our test. Let's try star repetition. Okay, so we're going to parse something with a star. A star is good enough to get started. And we will let the tree equal parser.parse. And I kind of want to assert well, as I'm going to say, it really has to be a in this case it's 0 or more. And I don't know, maybe node or tree. Okay, so I'm saying that this thing must be 0 or more tree, and if it is, okay, it's really it's got one child. Okay, let's assert equal, and then the child tree.child should be tree.child.value should be A. Okay. So we'll parse this tree with a star in it. We expect to get a particular tree back. This tree has a child node, and the child node should be the node we're looking for. So it should be this A. Okay. We got to get compiling first. So let's make up a new type. And this is 0 or more tree. Extends tree. Okay, and he must have a child child beneath him. So he has a child of type tree. Okay, so we're saying it contains something of any type. It doesn't have to just be a factor or a letter match, but has that automatically. Okay, and then we'll initialize this. Init, we'll give it the child of type tree. And we'll just do self.child equals child. Okay, so for a repetition operator like that, all we need to know is what are you repeating. Okay, we know based on your type, you're a 0 or more tree. We know that you do repeat everything. So let's run this. Should fail. Okay, parser.parse is going to get some other type. Okay, yeah, we get an abort. Okay, because right now our parser only returns letter matches. Okay, so let's revise it. Okay, so the grammar for unary operator is factor followed by a star. Let's just minimize it for now. Okay, so expression is really a unary at this point. Let's say we want to allow that, and unary produces a tree like everybody else. Okay, and you go in there, and the first thing you want to do is let child equal, and we're going to call factor. Okay, so first thing you do is always call, well, you replace any method. In this case, unary has the word method, or the factor there is a method that should call this factor method. Okay, so we'll do that. Then we'll look for the star, and if we find it, we will use it, and then we'll grow and handle the repetition and the pluses and question marks and so on. Okay, so we call that, we get the child is a factor. That's a tree. We don't know what kind of tree, because it could be parenthesized something else or whatever. But okay, so child is factor, and then we are looking for, let's say, if the character is equal to a star. Okay, so when we finish factor, we're left with the character being ready to read for the next thing. Okay, if it is, then we're going to consume it like we always do. All right, and then now, let's see, let's call this result for now. Okay, so we're going to have a result if you actually have a star. If there's no star, we just return the tree we get. But if there is a star, we want to return a tree that contains it. So we want to return, let's let result equal, and then our new tree, 0 or more tree, with the current result. So we got the factors result. Now we're going to wrap it in our type. Immutable result, var, and then don't use that there. Okay, we get that, and then eventually we return result. Okay, so this thing, I believe, will pass the test. Okay, nice. Now let's test the star. Let's test star repetition. Okay, so I'm going to do the same kind of thing. The parser, it's going to be a star star. All right, and we're going to get back this tree dot. The parser dot parse should be a tree, and we should. We know it's a 0 or more tree, that's fine, but its child should also be a 0 or more tree. Okay, so let subtree equal tree dot child. Okay, we know it's a 0 or 1 or more, or 0 or more. Okay, now the tree dot child, this should be the subtree's child. Okay, so we've got factor on the bottom, a star star, and so we get it back. We should have the first star should be a 0 or 1 tree. I need to do the same thing here. The subtree should be a 0 or 1 tree. Its only child, and then that thing's child should be a value that we say. Okay, And this should fail. Okay, I'll run them all. Okay, so the child failed the cast. All right, and the reason is we only take one star and then we're done. Okay, but the change for this is easy. We wanted stars to be able to repeat. We can just say while. Okay, so while we have the star is the next thing, we'll skip over the star itself and then build a new node with the new, the last result wrapped in a star node. Okay, and I think that should pass. Okay, let's handle the plus sign repetition. Okay, so this is the plus repetition, and then we'll do a plus plus, and I'm going to try and speed up the action here. Okay, so the parser is going to look at a plus. It returns a one or more tree, and should get the same thing in the inside. Okay, type doesn't exist. This should be the same type. Okay, and a plus plus. All right. And we don't have a type for it. So let's make this tree. And for now, I'm just going to copy this. One or more tree. Gee, it's kind of nice not to have to change the constructor name. All right. It's just going to be a tree that holds stuff. Okay. My tests should both fail. They should compile though. Okay, they fail because we don't have one or more trees yet, or we're not creating any. Okay, so let's go back to parser. All right, where's this thing? Okay, now we have to look for pluses, and I've got the two tests. I'm just not too worried about it. All right, so this inside, we're going to have to decode it though. All right. So I'll just use ifs for now. So if character is star, we're going to do what we did. Else, if character is plus, we're going to do something else. All right. Which is going to look very similar. Character start, we have to do this. We can't really do it until we look at the character, so I don't know, we can decide later if that's good or not. All right, I want a more tree with result. Okay, and I predict both these tests will pass. Okay, and I don't know if this test is adding anything. If that one works, I pretty much know this one works. And I think that's the same in this case too. So it got us going, but we don't need it for real. All right, let's add the next situation. Okay, and this is, let's just do question mark. Question mark repetition. And it's this. This is a 0 or 1 tree. And this is a 0 or 1 tree. The value is still A. All right. We don't have a type, so let's fill that in. Okay, basically it acts the same as these others. All right, and this should fail on the cast line as it did before. All right, I don't know why you don't want to do it on why you want to give me a new window for it, but okay. All right, let's get down here again. All right, so our next case is the question mark. And then this, else if character equals question mark. And we're going to do basically the same. But in this case, it's a 0 or 1 tree. All right, and should pass. Okay, so, all right. Let's take a chance and a moment and do some refactoring. So I'm going to say this is a letter match tree. Let's rename that. Just to kind of be consistent with everybody else. All right, and then these things, notice I was going to say they're very similar, but they're basically identical, okay? We're going to define a unary operator tree, a unary tree, unary operator tree. Okay, so let's make that public class unary operator tree is a tree. Okay, I think that should be legal. This should be able to be a unary operator. Let's make sure we're not messed up yet. Okay, the thing they have in common is this part. All right, and I think this should be okay. No? Cannot override with a stored property child. Oh, okay, let's just make them all. Take the big step. Okay, and run. Okay. This is good. It's a little, I guess the reason I was hesitating on it is I end up with these nodes that don't do much. These tree nodes. Their differences will show up later. It really is kind of important to know which operator you're dealing with. They have different rules for how they compute stuff. So I'll give you an example. One of the functions we're going to compute is skip, which says, can this node produce an empty string? And for 0 or more tree, the answer is absolutely. For 0 or 1 tree, absolutely. For 1 or more tree, it's like, could you be empty? Well, only if my child is empty. Okay, so, and rather than all being true, one of them returns something different. Okay, so back in Keynote, we've done this one now, and we've got the repetition and we've got the stuff there. So let's tackle term, and that's just sequential repetition. It's appending, basically. Okay, and I think we can just go from there. This is I guess it's concatenation with repetition. So if I have A, B, C, all right, my node will be I don't know, is concatenation the right word? Concatenation tree. Okay. And it's, let's call it left subtree. It's going to take I don't know, we'll call it, I guess they do matter, left and right, okay? So the left of this thing should be a concatenation tree. And the right should be our factor. Okay, so we should be able to see A is going to be subtree, left subtrees left, dot left dot value. Okay, we know left subtree is the concatenation tree. It's going to have a left and a right. We can work on my terms later. Okay, I should be able to find a B somewhere, and I should be able to find a C somewhere. So with this thing, it's going to look like, I'm going to put the node, here's tree, its first child is the left subtree is also a tree, and that thing has a, well, I'm going to live with the completion, and B, and then the third child is a C. Okay, so left subtrees, if you want the A, you go to left subtree dot left. If you want a B, you go to left subtree dot right. If you want a C, you go to tree dot right dot value. Okay, if we had a concatenation tree, so let's make that thing exist. Okay, so public class concatenation tree is a tree, and it's got two children. Let's say left of tree, right of tree, self.left equals left. Okay, and our test should fail. Okay, concatenation tree failed because nothing creates one. All right, so now we have parse goes to expression. Let's make file private function, what did I call it? Term? Term. Term produces a tree. Okay, and he certainly calls Unary, but we're going to call term here, and let's make var result equals Unary. Okay, so we'll take the subtree, and we have basically, okay, this one's a little trickier. All right, this is where the LR or the LL1 recursive descent thing comes in. It's like, how do we know if we're repeating or not? Well, the way we know is if the next character is a character that starts another unary. All right, well, what starts a unary? Oh, the characters that start a factor. Both paths have at least one character, so we don't have to worry about nulls. All right, and this always has a factor, so we know it's either going to be a letter or a parenthesis. And if we have those, we can repeat. And I think, yeah, we're fine to do that. So, and this is a while loop again. So it's we'll take this, and maybe we should generalize that at some point here. If it's less than that, if it's a letter basically, or it's a left parenthesis. Okay, if it's either of those two things, then we don't have to chew up anything because we are not responsible for parsing that stuff. We'll return result. Okay. It's not our job, so we don't have to skip over anything. We're just peeking ahead to see which way, do we want to take this branch back to ourselves? Okay, if it is, we want to get a second branch. Okay, so var, so we've already parsed the left. Okay. We'll take the right subtree. And that thing is, we find it by doing a unary. Okay. And we want to make it so result is always the current value. It's going to be a concatenation tree with result and the right subtree. I guess I got to say left and right. Okay, so I parse the first thing. If there's nothing following it except maybe end of file or end of string, I return it. But otherwise, I look for the right subtree. The new right subtree I'm going to create. Okay, and I do it. So let's see if this runs. I believe it will. The only thing I'm making sure I'm not tripped up by the ABC, but I think that should be okay. Yeah. All right. That timer bell was the timer for our Pomodori. So let's take just a couple-minute break, 2-minute break, something like that. All right. See you in a bit. All right, welcome back. I guess I should have asked when we started, like, are there people here who weren't here yesterday? And if there are, like, do you have any questions about what's going on, or is it kind of making sense so far? I think all we're trying to do at this point is really build up this big parse tree. And once we have the parse tree, we'll start populating it with semantics. All right, but at this point, I think, we've gotten through most of the grammar. Let's see. We're working on term goes to Unary. We've done all those down below. We just really need to work on concatenation, alternation. And what we want to do here, I think we really want to do the same thing we did down here. So rather than waiting for the duplication, I'm going to just pull it up right away. So let's make public class binary operation tree is a tree, and it really looks a lot like this. So I think we talked yesterday about preparatory refactoring. This is definitely an example of that. I can see where things are going. They'll be easier if I just do it now rather than create the duplication and pull it back out. It's legit to create room for the new change and then implement it. Okay, of course you have to do it correctly. Concatenation tree. Oh, we didn't inherit. Always helps. Okay. All right, the build's okay. Let's do the last one, alternation. So this is the OR bar. I'll say alternate with repetition. Okay. And this one is like A or B or C. Okay. And he should be an alternation tree. As should he. Okay. So the fact that we got the two trees, you have to go to tree.left. This is our grammar enforces left associativity. So that's how come that just sort of falls out. All right. So A or B or C, we want an alternation tree. Left subtree, right off of tree. Yeah. Should fail just like all the others on the cast. Oh, if you write that, yeah. You have to do this though. Alternation tree. All right, yeah, there we go. And we know what we got to do. In our parser, we have expression goes to term, but it really should be term or bar, term star, okay? So let's do like we did before. We'll say var result equals term. At the end, we'll return result, and then while there's a bar, I got used to leaving out my parens in Swift here. You don't have to, but it's nice. Okay, so while there's a bar, we're going to consume it, like we always do when we have a literal character we want to get past. And then just like the other one, we're going to make a right subtree. And it's going to be another term. Okay, so it's term or term. And let's see, we need to build a result. Alternation tree with left being result, right being right subtree. Okay, return result. All right. Yeah, stop the test. Okay, and now we're done basically. We can improve things a little, but I think, you know, I've got right subtree. I'm going to make this left subtree, even though sometimes you'll just return the left subtree. Is there a better way to do this? Maybe result is right. Yeah, I think I'm okay with it. We have the same situation in term. Notice the difference here. We have an explicit character. If we'd had a semicolon or a bullet or something to say concatenate, but we want to write things like AB star. Okay. But I think we are basically done with our parse tree. Finally, what does it do? So the big thing for us, parser, you call parse, you get a tree back. We have tracked errors, like missing right parenthesis or random characters and stuff like that. Okay. I'm going to say we really should be returning that as well. Okay, so we will put it in here, the tree and errors. All right. I don't think anybody calls parse at this moment. Let's return result and errors other than tests. So we may have to revise a couple tests. That build should detect that. Yeah, cast from parser.parse. Let's just do it like this. Ignore the errors. You not like that, huh? Okay. What's a good way to do this? Maybe I can push it out. I can't have two different returns. Let's go back to where we were in here. Let's put another function up here. I'm going to say analyze. All right. Because I'm trying to get the full capacity of it. And I want analyze to return tree and errors. Nobody's calling this yet. That's okay. But its job is to return parse and the errors. All right. So I'm making it easier for my tests to not have to fuss with the error messages when they don't need to. And I kind of do want to parse separately in some cases. Yeah, so I think if I rebuild, my test should run. My build failed. Who's out there? Oh. Okay, so let's push this. Syntax analysis is complete. Right? That's a good thing. Basically, parsing it into a tree is the part we're talking about. Now, our compiler is not really set up to use it yet. And that's a little bit of a problem. Let's see, where's the parser? Oh, parser is a function here. Yeah, so we've been very minimal here. All right. What we really want to do, and I don't know if we want to, what I want to do is I want to get parse to be tree rather than string. And I think if I just do it, it's going to break. Let's try a build. Yeah. Whoops. Is tree. Cannot convert return type of type string to return type parser. Because he's just returning the string itself at this point. I want to respect the structure we're getting, but it's not. So what I want to do, I want to say the parse and the errors, parse errors is parser dot, let's see, parser sub input dot analyze. Okay. Now is never used. Right. Okay. And then I need to merge in the errors to the errors I have. Okay. So errors dot, can I append contents of parse errors? Okay. And I don't know, maybe I'm jumping ahead of things here. Okay. The real thing is this parser method. Okay, I think that's gone away. Is anybody calling it? Cannot convert tree to expected type string. Okay, so his input is a parse. I really want his input should be a tree. Okay, let's get that much straight. Cannot convert tree to expected argument type string. Return intermediate code with original expression. And what is he doing? I thought this would be bubbling types through, and it seems to be becoming more than that. Okay, so intermediate code. Let's look at this thing. The real thing is we don't do anything with this yet, and I'm like testing around it. So the generate intermediate code, it should take the parse and the suitcase and produce intermediate code. That's true. Tree and suitcase. But this is TBD. Like, how do we generate? What is this intermediate code? We haven't really said. I just said it's a string. And our trees don't really promise to have values except for the leaves. Okay. I'm going to hard code this for a moment. And I just see how many tests break from that. Because we're not done with the analysis part. Oh, I want to run tests. Okay. I think there'll be... Okay, so yeah, generate intermediate code. Let's make this a letter match tree. I don't know if we can okay, I don't know. It's a string. It's a little funky. Okay. Is this good or bad? Where's this coming from? I mean, I think it's back in here. Okay, we did get rid of this. All right, no input found. If the input count. It's almost like we don't need that. That's not going to change the answer, but I think I can live with the other code for now. This thing, let's just change it. What did it look like a minute ago? I don't know what that is. Oh. Okay. Clunky, but progress, I guess. Okay, so we have, when you run the parser over some input, you get a parse and you get some parse errors, and then we pass the parse on to the intermediate code with the suitcase. I honestly think our parser should be producing the suitcase, but we'll get that together shortly. Okay, let's check in. Make compiler use tree from parser. Okay. So now we're finally through the sort of matching stuff that is built into this, and it's time to get stuff that's specific to the algorithm we're working on. So yeah, I know we spent a good couple hours plus on that, but the first thing we need to do is there's this notion that we assign numbers. So any letter, any final match character gets a number with it, and we also need to know the maximum number. All right. And I think our strategy is going to be attach that number to the letter match node, letter match tree. And we'll let the parser maintain the count. Okay, so where's parser? All the way over. All right. So parser. Okay, so let's test that nodes know their position. I think that's what that's called in the paper. All right, so if we made a parse and we parse AB, and we have to have both in the same string, so that's the way it goes. Let tree equals parser.parse as a concatenation. Okay. All right, and we'll let left equal tree.left and right equals tree.right. Okay, now we're kind of ready to assert some things. We pulled left and right. We know that left, let's see, this is a letter match tree, and so is this. Okay, and so we want to check that the left one's index is 0 and the right one's index is 1. I'm sorry, the left is 1 and the right is 2. So assert equal 1 should be left dot index position, and 2 should be right dot position, and then we want to know the count, and this is where well, the position field doesn't exist yet, so that's not a problem. But I would like to say parser, I would like to say the count is parser dot, I don't know, count, position count. Okay, so this 2 I need to come out of be set in the parser. Okay, and so I need a position in my tree, my letter match tree, which I probably want that thing down on the bottom. So here's my binary operators, my unary operators, and my, what are they? Nonary. I know that's not the right name. Forgive me. Okay. We need a position. This is really, it's known when we create the node. Position of type int, and you have to be prepared to well, we'll initialize it for now. I won't leave it this way. Okay, just to kind of keep things moving. Position int. Okay, and then the parser is supposed to have a position count. Okay, and it starts off 0. I guess we're saying you're going to start it at 0, you're going to increment it, and then save it. Okay. Test should fail, but compile. All right, so we got -1, -1, 0. All right. Okay, so our only place we create these letter match nodes is here. Okay, and let's make the letter match take the position. Position of type int, and we're going to say self.position equals position. Okay. Whoever calls a letter match tree needs to be specific. Okay. So position was 0. I'm going to say position plus equals 1, kind of accessing a class level variable, and position is position. Okay. I'm going to have some build failures on the test side, I think. I don't know if we created a letter match tree directly. Immutable value. Okay. All right. Okay, I knew somebody had to do it. Letter match tree. Let's make position 1. We don't really care. Okay. What's going on? Alternation tree. All right, what have I done? I've got letter match tree still. What tests have failed? A or B or C should be an alternate tree. Position. I don't think I was using position. Oh, position count. Ugh. I've got position as the position of the character in the thing. That's confusing. I've done it again. Position count. We talked about separating out the lexical analysis, breaking out the tokens, letting them keep track of the positions and all that stuff. Okay. So this is good. This is exactly what we want. Excuse me. All right. So I think with all that set up, we've done this. So you can ask the parser what the max is, and it will tell you. Maximum is 2 in our case, 5 in this case. All right. So the parser. Now this is where I was talking about the suitcase. I really think the parser should be producing the suitcase. So the parser right now, it produces the parse tree and the error messages. But the fact is, in most compilers, for programming languages, there's a symbol table that comes out as well. And the symbol table is, what are the variable names you used and how are they organized and all that stuff. It's not the parse tree. It's a summary of it or other characteristics or things like that. So, in our case, the suitcase is the other stuff. It's not a symbol table. But it is like it knows what was the original input string, so I can put it in the code as expression, and then I can display it on the screen up top. Okay, so that comes from the suitcase. This is supposed to come from the parse tree. All right, but the parse tree, we probably need that position count. I don't know. We'll keep our eyes open if it's a problem, but really it should probably be in the suitcase, I think. But okay, we'll move on. All right, so where are we at? So we've got the position indexes. Now we're going to compute the skip function. So we want to say if you've got a letter, you can't be an empty string because you're a letter. Okay. These rules are actually pretty intuitive. Okay, so if you're matching a letter, it's got to be non-empty. Okay, can you skip it? No, it's false. If you've got a alternation, we're using a bar, E1 or E2. Well, if you can skip E1 or you can skip E2, then you've got a path through that allows skipping. If you have E1 followed by E2, you're only skipping if they both can skip. 0 or more, yes, you can skip. Plus, which is 0 or 1, you can only skip if you're inside skips. We mentioned these, and question mark 0 or 1. So we're going to build a node, we're going to build stuff and then just make sure that this skip works. Okay. Golly, can I do it? I'd like to do it in fewer tests if I could. Okay, so I would like to say that a letter match knows it can't skip. How about letter match skip is always false? All right, and now I'm really testing the tree. Okay, so maybe I got to break this out a little bit. I've got, yeah, let's do a class tree tests. And we really need to split these files at some point. It's XC test case, and that is in there. Okay, so I want to say that letter match tree of value position X, position 1, I want to say XCT assert false. Can it skip? That skip, maybe, let's move that down a line. Let's let tree equal that, and then assert false tree dot skip. And actually, it's really a property of the thing that's in the tree. Okay. Excuse me. So if we look at the rules, what you should notice is any node, the rules for that node only depend on the children. Okay. And so when we create the node, assuming the children are already created, which they have to be, we can answer this question right away when we create the node. All right, so we're going to do that, and we're going to give a skip function. I'm going to give it a default one. Okay, so just var skip of Boolean equals, and I'm going to say this is false. Can you skip? So let's make this true by default. We'll probably flip it the other way in the end, but our test should fail. Okay, our assertion failed, and now we want to make letter match tree. Okay, so basically, when you create this thing, if it's a letter match, you know it's false. Okay, there's just no way around it. Okay, so let's, whoops. Okay. We have this thing in Swift, defer, and you can use it to initialize stuff once you're through the rest of the constructor. Self-using method. Oh, I just didn't call super init. Maybe I don't need it. If I call super.init, ugh, my value not initialized. Super. I think I do want this defer stuff. Position is a let constant. I don't understand why I should need this. Is that going to be acceptable? No. Self.myValue not initialized at super init call. That is correct. Okay. Cannot assign to a property. We'll make this a var. Self.myValue not initialized at super init call. Can I do this before? I'm used to having to call super init first, but Swift's a little different. Let's see if this is acceptable. Okay, I'll do a build. Okay, a little weird. Do you pass? Okay, so we'll commit this. Letters never skip. Okay, I gotta admit, this looks a little weird to me, but that seems to be what they require. The bell was another break for us, so we'll take a final break, 2 minutes, and then we'll come back and finish this skip. I think we'll have no trouble finishing that pretty quickly, and we'll see if we can get the out function figured out as well. All right, see you in a couple of minutes. All right, welcome back. Let's see. I do still wonder. I want to see if these can be lets because we are setting them right away. We don't want to change them. We don't want anybody else to change them. Okay, let's go on to the next one. So function 0 or 1 skip is always true. And skip is like can skip. Okay, so let's take this thing. This is assert true. All right, and now I'm going to change my default just to kind of force the test to fail. All right, let's run these tests. Should fail. Okay, and 0 or 1 skip. 0 or 1 tree. Well, we'll do init. How is it handling that? It says var. I wonder if it can be a let. Oh no, maybe at the end we'll do that. Okay, so 0 or 1 tree. Let's let the unary operator tree deal with it. So let's add the other case that we know is a false or a true. Zero or many. Skip is always true. Oh, and this should be a 0 or 1 tree. And this is a 0 many tree. Zero or more tree. Okay. Both those should fail. Oh. I don't need values. I need a subtree. Ugh. Oops. And it may be to the point where it'd be easier to get the parse going, but okay. You're supposed to give me little test runners there. I gotta call it test 01. Test 01. Okay. Okay, so I'm going to default the operator. I think if I do self.skip equals true by default, I think that's how I was getting a build error before, right? Yeah, so I got to call super init. And then initialize the super fields. Okay, I think my 2 tests will pass. All right, now let's test our last of those factor unary operators. 0 or 1 skip is true if child skips. And I guess I got to test both ways on this one. 0 or 1 skip is false if child does not skip. Okay, so a child that skips, if we had a 0 or 1 if there was a 0 or many tree, beneath it, so we got a 0 or 1, so we basically got X star question mark, except I don't have something. 0 or more. I keep calling it many. Okay, and in this case I've got the child does not skip. Okay, so skip is false. All right, now I expect one of these to pass because the hard coding on the unary operator, we said default is true. Okay, and we're saying there's a case where it should be false. All right, so this is the 0 or 1 case. Oh no, this should be the one or more case. One or more tree. All right. Okay, 0 or 1. Skip is false. Sorry, this is one or more. Ugh. Okay, one or more. Skip is true if child skips. Right. It's false if the child does not skip. Okay, I think I'm saying it right now. My confidence is not so good. Okay, that's the one we expected to fail because our unary tree says skip is defaulting. Okay, so now we need to call init. What do we want to do here? Yeah, I guess we're going to say init with a child tree. You're going to call super init with the child. And we're going to say self.skip equals. All right. And then this is where we got to look at the rules, right? The rules here, it says this your skip is the same as your child's skip. This is the one or more case. Okay, so your skip is child.skip. Okay, override. Expected expression in assignment. What does that mean? Okay. I believe this will pass. Okay. Now we want to test. I guess we got to go on to. We've done these 3 rules. We've done the first rule. We got to do these 2. So the skip and skip for the concatenation test. Okay. Test concatenation is true, false if both children. No, it's true if both children skip. Make double check our rule. Okay. If child 1 skips and child 2 skips, then we skip. Okay. So let's set up a case. And I don't know, I'm getting I'm starting to feel like I would like to just get a parse and be done with it. So let's try tree equals parser of both children skip. So A star, B star, even B question mark. And we should be able to say XCT assert true tree.skip. Okay, so we know it's a concatenation tree because we've got A star followed by B star tree. Oh, dot parse. Okay, so we got A star concatenated with B star, B question mark. Question mark, we already proved skips 0 or 1. Okay, A star 0 or more skips as well. All right, and this should fail, I think. I lost track of if we have a default and what the default is. Okay. And let's add the other test as well so we can function concatenation is false. This should really be skip is true, skip is false if any child skips. Okay. If any child does not skip. All right, so A star B, the second child, is a letter, so you know you're going to get at least a B, possibly some A's in front of it, but in either case you can't skip. So this is assert false. All right, so I want to make sure both these run at the same time. I don't want to get some mode where I'm flipping back and forth. Okay, and this is the concatenation tree. I'm just going to move this down. Just trying to get them kind of in the order they show up in the grammar. So concatenation tree, it needs to initialize with a left and a right. Basically this. All right. And he's certainly going to call super sub left, left, right, right. Okay. And I don't know, did one or both fail? Okay, this one sort of passes already. We must default to false at this point. Okay. Expected dot after super. Super init. Okay. And now we can set our skip equals left dot skip and right dot skip. Okay. And that's again back to our rules. So let's run all the tests. Okay, now we got one more. Alternation. All right, so alternation. Skip is true if either child skips. And alter. Skip is false if both children do not skip. Okay, so skip is true. So alternation, we need a bar in there. Okay, if we take A star B, we got either child. One child skips, the other doesn't, but the alternation could skip in that case. And in this one, we got A star, both children do not skip. Let's just do that. All right. These should, at least one should fail. Sorry, true failed. Okay. I'm just going to steal this. Okay, so the skip is left sub right or right dot skip. Okay, so if either one is true, the whole thing is true. So if either child can skip, the whole thing skips. All right. Come on, test succeeded. Okay, everything's green. All right, I'm going to call this class tree skip tests. I think we can make another class for the other case. All right, so a lot of setup for parsing, and then the analysis is really straightforward. So that's the reason we like to do the parsing in the first place, because once everything's in trees and things depend on their children, they just bubble up real well. Okay, so let's go back here to the grammar. We got the skip function. We did that. Next page is the out function. All right, now this one, we have sets of integers. All right. So the question it's answering is when you finish walking through this item, when you finished with this, whatever tree or subtree it is, what positions could you be in? All right. So let's go back here. When I finish A, I would be in position 1. Okay, I've got this term A, A1. Where could you end up after you've done that? Okay, only in A. But if I take the alternation, okay, well, concatenation, AB, if I go through this whole term, AB together, I could be in 2. If I do AB or B, I could be in 2 or 3. Okay, so they continue on, and same thing with the star. I could still be in 2 or 3. Oops. Let's see. So next page. There we go. All right. So we got rules for the out function, and the simple one, the factor one, is the simple one again. Okay. So these are tree out tests. They're an XC test case. All right, and we got a function test letter match yields its own position. Okay, so the tree is well, let's just do this parser thing. It seems easy enough. I don't know. I'm building a little dependency because it's the fast way to get a tree back out. Okay, especially for the more complicated expressions. But if I've got the string A, its position is 1. Okay, and so I should be asserting 1. Actually, the set. I think it might infer it if I do this. The set 1 should be tree.out. Okay, out has no members. Yeah. So we're adding more to our tree. It's growing up. It needs an out function. Out, and that is a set of integer positions. Okay. And we'll start it off empty. Okay, this test should fail. All right, so 1 is not equal to empty. Okay. I don't know if I pushed already. I probably missed a chance. We'll do it in a second. Let's see. So out, and we want letter match. All right. So we know in letter match, the out is always just the set of the position. Okay. So it's a constant value there. All right. Let's run all. All right, let me look at parser. Maybe I did push that. Oh, no. Here we go. Okay, so the skip function. Compute skip function. All right, and a little bit of out. Okay, next one. Take a peek. Out of, well, let's do the easy ones again. They're the same as their child. Okay, so those unary operator ones. Code all the way over. Okay. Let's say function test. I don't know, is this too obnoxious? Unary operation yields its child child's positions. Okay, so if I have a tree parser of a question mark, its output, it really should be this. Okay, it's just referencing its child's value. Value of parser.parse. Okay, expected. Yeah, good point. And this should fail. One is not equal to empty. All right, so the unary operations, and you know this could change, but we're really saying self.skip equals child. Oh, sorry. Self.out equals child.out. Okay. And I think we're okay. Now I could write all three tests. You might wish I had. I don't know. Anybody screaming? Let's see. Code Wrangler. Yeah, thank you, Code Wrangler. Catch you later. And there will be videos up at Twitch there afterwards. All right. Let's see. So we're up to these concatenation alternation, right? So concatenation, well, it's harder. We'll do it. The concatenation, it depends on whether skip is true or not. Okay, so it's got some complication there. So let's say test concatenation yields well, let's yield right child if, well, it yields union of position if the right child can be skipped. And nobody can ever get to empty because we don't allow empty strings for our regular expression, I guess. Okay, so maybe, I don't know, maybe I want the easier case. I got to do them both. It's the union of the two if you can skip the child. A union of children if child 2 can skip. Okay, and the other test is test concatenation yields child 2 out, children out. If child 2 cannot skip. Am I saying that right? Use the union of the two children if the child 2 can skip. It uses out 2 if child 2 cannot skip. Okay, so we'll parse. Okay, we want something where child 2 cannot skip. So let's make A star B. That definitely has child 2 cannot skip. Okay, and the positions are 1 and 2, so that's easy to calculate. We'll parse, all right, and we're going to assert equal. We want the set yields child 2 out, so that's just 2. If tree.out. Okay, so child 2's output is 2. Child 2 cannot skip because he's a definite character, so that should be that. Now this case, Yields union of both children if child 2 can skip. Okay, so if I have A, B optional, child 2 can skip, and then my assertion is I expect to see both children, which is 1 and 2. Okay, and this should fail. At least one of these should fail. Whoops. Parser. Oh. Yeah. At least one should fail. All right, both fail. Fine. And they should be equal not to blank or empty set. Okay. Where's our concatenation operation? So his out, okay, out equals, okay, can child 2 skip? So the right dot skip. If that's true, it's the union of the two. And boy, there's a way to do this, but let's see. It's left dot out dot, and there's like two union things. Union other. A new set with the elements of both. That's what we want. Is left dot out dot skip. Sorry, left dot out union with right dot out. Otherwise, it's just left dot out. Oh no, it's right dot out. Now, these things don't change. Let's see. Once they're made, they don't change. So I think the semantics, the semantics of arrays in Swift are copy it. And every copy of an array is a copy, I don't know, it's kind of copy on write, I guess, or something, but it's effectively copied when you assign them. I don't know if this does that or not, but the union creates a new set, so that's what we want. The right dot out, we're never modifying these, so there should be no harm, even if it's pointing to the same set. It's okay. All right, let's check this. Right, and one last function. Test alternation yields, I think it's the union of both children, right? Because you don't know which branch you're taking, so either branch should get you there. Yes, union of both children. Union of both children positions. Okay, so a tree is parser A or B, and we're going to assert equal. We expect to get 1 and 2 both in there in tree.out. Okay, so hopefully this makes sense. And again, I'm going back to the position stuff. So if I have A, B, or B, all right, if I can get to position 2 or I can get to position 3, depending which branch I took of this alternation, at the end I'm going to be in 2 or 3. All right, so there's no question about it. All right, so this is all kind of like the heart of what this thing is doing. Okay, so should run, should pass. Oh, should fail. We haven't failed yet. Okay, it's not equal to empty. Right. Okay, so alternation, we need to, it's always the union, so that's okay. So self dot out equals left dot out dot union with right dot out. Okay, let's see. So we've calculated the out function. Okay, and notice this is a function of each subtree. You know, as you're going through. So each one of these has its own version of where could you end up after going through you. All right, let's go on. Well, we're going to go back to our big set again. Okay, so the stuff we've done so far, these three functions, the counting, the skip, and the out, they're all pure functions of their children. This one gets different, and this is what drives our code. So I'm going to spend a minute on this this structure. So what this function is answering, it's let's see. So notice what I got. I've got trigger of a character in this H is a position. Okay, so if you traverse this, can you go to this position? All right, so let's start up here. Okay, so the trigger, here's the traverse. If you see this in position 0, 2, or 3, go to position 1. All right, let's go back down there. Okay, if you see AI, well, if you're at AI, you can always get there from 0, I guess. So we're going to call this thing with 0, but as we go through, we're kind of we're basically building off of our out function. Okay, so our triggers and outs are both involved in this computation. And we notice we have a integer and a character and a set of integers. Okay, the set of positions. So this is the position of something, a character, and the set of positions. So if you see an A in position 1, you can go to 0, 2, 3, and based on our calculations. If you see an A in position, and you're in position 1, you could have got there from 0. Well, let's see, more this way. If you see an A and you're in position 0, you can move to 1. If you're in position 2 and you see an A, you could go here to position 1. If you're in position 3 and see an A, you could go to 1. Now, if you're in any other position, let's see, if you're in position 4, can you see an A? Oh, you can go to 5. But there aren't any other places that can get to an A legitimately. All right, so we see 2 rows for the A situations. There's only 2 possibilities. You either get to 5 or you get to 1, you know, after reading an A. And then B, if you're in position 1 and you see a B, the only way you're going to get there is on your way to position 2. Okay, because we've already committed to the A, and the only way out is to take the B. All right. If you want to like take a screenshot, I'll give you 3 seconds. 1, 2, 3. You know, this function, I think out and skip makes sense. This function you got to think about, and that's just the heart. That's the whole thing of this paper. Like, computing this function makes you get all the benefits of the code generation. All right, I'm going to bounce to that code generation. I don't know if I can get it side by side. I'll just copy this here and put it over here. Can I make it? You're just not going to help me, are you? Okay. Anyway, in here you can see the state 0. You go to start at, you go 1. Okay, maybe this is more interesting. If you're in state 1, or I'm sorry, you can go to state 1 if you see a 0 and you're in state 0, 2, or 3. So the next state is saying, where can you go next? All right. If you're in state 1 and you see a B, it's definitely good. You definitely can go to state 2. Okay. But if you're in 1, if you're in 0, 2, or 3 and you see a B, you could go to state 3 and so on. Okay. So I copied that, right? So take this out. All right. So I hope that makes some sense. It's a crazy thing. All right, let's go back to our compiler. This is what I was thinking of as the intermediate code, by the way. So when I say intermediate code, right now, what are we saying? Original expression code. This code of string, that's just stuff we were pushing through to get building. Really, what I want is I want this trigger function, okay? Triggers. And this thing is, well, I said the type, it's like a set of triples. Let's go back. It's a set of this stuff. That, okay. Oh, is it character? Yeah. All right. So I don't know. It's does not conform to hashable. Okay, so we're gonna have to make our own little class for this. Let's just say int for now. I'm gonna make a. I guess we'll get the class defined first, and it's going to be a class because I'm going to change it. And this is triggers. Okay, and I don't know. Do we have names in these things? We don't really. So I is always a position. H is always a set. Let me just. Well, we'll put them in the same order they do. I guess that's okay. But I feel like something's. Okay, H is definitely the set because that's the one that's getting unioned here. Trigger, this whole thing is a set as well. Ugh. So the trigger row is the set, the stuff in the parentheses. Okay, let's make a definition there. Trigger row. Okay, it's got a position of our position. Actually, it's a let, really. Well, we'll say var. Var position of int. It's got a character. Character of character. And it's got a I don't know what we want to call this. It's really a set of positions. I mean, oh golly. It's this position set. Maybe this is the move to position or something, and this is the positions. Moves to. Let's try that. It's an anonymous name. Moves to position, These things are positions of type set of int. Okay. Then the triggers as another class triggers, and maybe I just need set of trigger row. Maybe that's enough. Let's hope so. Okay, well, let's go to initializer. Init moves to int character of character and positions of set of int, and we'll just assign moves to position equals moves to self.character equals character, self.positions equals positions. Okay. That's probably good enough for now. So we'll stop here, and we'll pick up tomorrow, but we're going to get this trigger function done. Hopefully it won't be too bad. I mean, it's like the other. There's just a definition, and we just have to make sure the pieces follow from that. We'll get this trigger function working, and then we'll get the code generation going. So my hope is we can generate a basic version of code from these triggers tomorrow as well. So we'll see if I get any more behind. You know, I'd kind of like to be a half hour ahead of where I am now. If I get behind, I may have to go into some sessions next week, I guess, or something. Maybe Friday. I'll have to check if I can do it Friday. But I think we can get to a definite point with this. Now, if I could just... okay, I'm gonna... I'll just finish this thing is set of trigger row, and we'll make that add in. Okay, so that should be enough to compile, and we'll pick up there. So thanks for joining me today. We'll figure out what these errors are and go from there. So catch you in the future tomorrow, 1 to 3 p.m. Thursday, that is Eastern time. And thanks for joining so far. Bye bye.